certainly for the rest of today's lecture. We won't get to the running. We'll do that next time, but we'll at least perhaps get to the point, I think, where you'll see why that operator is showing up in DIS. Okay, so let's do DIS. So I'm only going to talk in DIS about factorization. And then the renormalization group evolution. So no phenomenology, nothing like that. We'll just talk about these two concepts. So DIS is electron-proton to electron anything. So just kinematics. Think about a virtual photon exchange. Proton comes in. I'll say that the proton's momentum is a capital P. Gets blown apart. Call this stuff it's blown apart px. And so px is the sum of all the particles, all the final state hadrons. Q squared of the virtual photon, so this is Q. Little q squared is minus capital Q squared, and this thing is much bigger than lambda QCD. Bjorken X is capital Q squared divided by this dot product. And you can talk about Px, which is the Px mu. And by momentum conservation, that's the proton momentum plus whatever momentum came in from the leptons, Q. So Px squared, if you square it, well, this guy is giving you mass of the proton squared. And then there's a cross term, and this guy squared. And if you put those things together, you can write it like this. So this is an exact equation. Px squared is that. And so there's actually different regions of DIS, and we're only going to talk about one of them. But I have to enumerate what I'm talking about carefully. And I can do that by looking at Px squared, or this factor 1 minus x over x, which I'll call 1 over x minus 1. If this thing is of order q squared, then that means that this thing you're counting is of order 1. And in that case, it's what's called the inclusive operator product expansion. So this is the case that most books would deal with. And that's the one we'll deal with, actually, where effectively we're not putting restrictions on x. We're just saying it's generic, and it's not approaching any endpoints. There's also a situation where the px gets smaller, and then this thing is close to an endpoint, lambda QCD over q. And that's called the endpoint region. And people talk about that. Usually when people say x goes to 1, this is what they mean, that the 1 minus x minus 1 is of that size, lambda QCD over q. There's even a third region where the px squared becomes hadronic, lambda QCD squared. And that's like here, 2 powers. So taking that factor to be really small, and that's kind of the resonance region. And that's the case where the final state x is just another proton, or an excited state of a proton. So that's where elastic scattering would be. And exclusive, that's an exclusive process. It's not inclusive anymore. So actually, all 3 of these cases can be done with SET. And the way that it works is different in each case. And the case that we'll do is just the first one, which is kind of the classic one, and also the simplest one. So our px squared is going to be of order q squared for our analysis. OK. We also need some partonic variables. So the struck quark carries some momentum fraction from the proton. This is the familiar language. And for our analysis, what we're going to do is just take m bar dot little p of the quark to be something times m bar dot big P of the proton. So the fraction is this c variable, and it's the ratio of the quark momentum to the proton. But we'll do it in a very particular component, and we'll see why that's the right thing to do. And if we have a picture here of the quark kinematics, then this P is the incoming P, and the outgoing P would be P prime, let's say. So I could think about an analog of this equation where I square P prime. And if you do that, it's kind of similar to the hadronic case. The only difference is that the C shows up. So, and of course, there's no mass of the proton. So P prime squared would be that. OK, so we'll see how this variable c shows up. Now, one thing that we have to decide about is frames of reference, because remember when we're talking about degrees of freedom in SCT, we picked a frame to do that discussion. And it was almost always the center of mass frame so far in our discussions, or the rest frame of the initial state. And here we're going to use a slightly different frame, which is sort of the most convenient frame for deep elastic scattering. It's called the bright frame. So we're going to do our analysis in this frame. So what defines this frame? This frame is defined by taking Q, mu, to just have a z component. Remember, it's space-like, so it has to be somewhere in the space-like column. And we can choose it such that it's entirely in the z component and nowhere else, and that's the bright frame. If we want to write that in terms of our sort of classic decomposition of n and n bars, we can write it as a difference divided by 2. And that's giving the z component. So in this frame, what's happening is that your initial state proton is coming in with a very large momentum, and then it's being sort of, you're kind of killing that momentum and then spitting it back out in a different direction. So you're spitting back out stuff in a different direction. So the initial state proton is coming in with a large momentum in some direction. So if you work out the kinematics given that, for what the proton would be, the proton's momentum would be of the following form. OK, so it's got a large, this is large, and this is small. And if you have a large component in some light-like direction, that means it's collinear. All right, so you could actually write it as, using momentum conservation, you could write it like this. And it has a kind of collinear scaling. So what we have in deep inelastic scattering in the bright frame is that the incoming proton is a collinear proton. And if we look at px, and we just, again, I'm not going through the details of this, but if we just decompose px in terms of these coordinates, then we get this. And so as long as this factor 1 minus x over x is of order 1, you see that there's a large component in n and a large component in n bar. And that means it's hard. So what would happen in these other cases here is that you would change that, right? It would no longer be hard, and that's why these cases here are different. But as long as we're in this first case, this is hard, and we can say that we have clear modes and hard modes, and then we just want to write down an effective theory for those two things. You could also do an analysis of DIS in the rest frame of the proton. That's another case, and actually the final result that you would get would be the same as what we'll get from this frame, but this frame is actually a little easier. Okay, so we're really talking about hard collinear factorization in some sense. Collinear describes the low energy degree of freedom, which is the proton, and hard describes the off-shell final state and the hard fluctuations. And really what we want to do in DIS in this classic case is just separate hard and collinear fluctuations, at least in this frame. So we can do that for the cross-section. So let me remind you something about the cross-section in DIS. So just using nothing more than the fact that we're treating the leptons order by order in the photon, we can work to first order in the electromagnetic coupling, and then we can write down a formula like this, where we split it into a leptonic and hadronic tensor. And the hadronic tensor can be written as the imaginary part of some T, where T is the following thing. So this doesn't use anything about, we haven't used any sort of perturbation theory or anything to write this, what I'm telling you down. We just work to all orders and basically use the optical theorem. So T is the time order product of the two currents. Let me call this Z. Actually, I don't know if that's... OK, so that's, before you start doing anything in QCD, that's how you could write this, and these are the electromagnetic currents for a quark. Thanks, yeah. OK, because X was something else. Don't want to use X. All right, so for this T mu nu, we can also use current conservation and decompose it into two pieces. So this is a classic thing that we do in DIS, and nothing about the fact that we're using the effective theory really changes doing this. What you're after, the effective theory is calculating these T's, which are the coefficients. So this part is all standard stuff for any analysis of DIS. So if you're not familiar with it or you don't remember it, it's actually not that important. But using the current conservation of T, the fact that when I dot a Q into the T, you should get 0, because you're dotting a Q into the current. Current is conserved. It's electromagnetic current. That tells you the possible structure of this thing, and there's two general terms if I'm doing a spin sum, which I am. OK, there's a sum over spin up there. If we weren't summing over spin, if we were picking out particular spins of the proton, then the formula here could be a little more complicated. All right. So this satisfies all the symmetries. And in general, what you know is that you want the imaginary part of forward scattering graphs. So pictorially, it's sometimes useful to draw something. So here's a forward scattering graph. And the thing that's different that we know now, and the kind of information is that we're going to use, is that we're assigning the external guys to be collinear and the intermediate guy to be hard. So we want to integrate out the pink guy, as usual. Okay, we want to integrate out, as always, pink. And we want to keep these collinear guys. Right? And so the operators in the effective theory, we can already intuit what they should look like. They're just going to involve kind of a current with two photons hanging out of it, and then collinear quarks. Those are the external lines there. And there's actually also an analogous thing with collinear gluons. And that's what the type of, so I could have an operator at higher orders where the external states here were gluons. And that's what the operators of the effective theory are going to look like. Okay, just contract that pink line to a point. That's what they look like. So given that we know what they look like, we just have to write down the lowest dimension operators of that form. And the lowest dimension operators of that form are exactly the operator that I told you was going to be the one that comes in. So we can enumerate the lowest dimension, where dimension here is counted as lambdas, right? So it's the lowest order in the power counting operators, so not the lowest order in mass dimension. Let me kind of write out a few things. I already switched to this notation. Yeah. Okay, so the type of operator we'd have that's order lambda squared. This guy's order lambda, this guy's order lambda, this lambda squared. And the most general thing we can think of is this. Okay? The reason why I wrote this out rather than writing it as a chi field is I wanted to emphasize that there's a flavor index. So I is up quarks, down quarks, strange quarks, etc. And then we could also have gluons. And gluons is similar. Except in terms of our curly V field. And it is actually just a contraction of two curly V's. And then traced over. And then there's some Wilson coefficient here, which is also just the Wilson coefficient for the gluon. Okay, so this is, again, order lambda squared. The B perp field is order lambda squared. So we just write down the lowest dimension operators that have this form, and that's going to be the right answer. Lowest order in lambda. So it turns out, actually, that in this case, our lambda counting is exactly corresponding to twist expansion. I'm not going to...
OJs correspond to the operators that go into the T1s and T2s?
Yeah, right. So now what's the index J? Exactly. There's a T1 and a T2. And the T1 and the T2, although they have the same kind of quark and gluon field structure, they get different coefficients, and that's what the J is. So when we think about doing a similar kind of decomposition in the effective theory, we can write it as follows. So as an O1 and an O2, and I think if I'm getting my mass dimensions right, it looks like this. So there's a piece that multiplies a spin structure that's this G perp mu nu, that's transverse to Q. And there's a piece that multiplies this guy, which is also transverse to Q in the bright frame. So that's the kind of decomposition we would do in the effective theory. There'd be two different types of operators we could think about. But the only thing that actually tracks that, because of kind of the spin relations, the only thing that tracks that is the Wilson coefficient. So that will differ in these two different cases. OK. So this guy here is going to be, this will give the quark PDFs. And his Wilson coefficient will then be the thing that you convolute with the quark PDF in DIS. And then likewise, this guy is going to give the gluon PDF. So let's do the quark. We'll do the quark contribution in detail. The gluon contribution is not really any harder. So what I'm going to do is I'm not going to think about it in perturbation theory. I'm just going to think about it to all orders in perturbation theory. And really what that means is I'm not going to think about this C as expanded in perturbation theory or think about any of the diagrams here as expanded in perturbation theory. I'm just going to see if I manipulate things, what does it lead to, using things like momentum conservation and stuff like that. So let me write, in order to do that, let me write it slightly differently than I just did, which I apologize for. But I want the arguments of the C, for a kind of later convenience, instead of being W1 and W2, to be W plus and W minus, the sum of the W's and the difference of the W's. So everything else the same. It's convenient to just talk about the sum and the difference rather than the individuals. OK. So what's the part-time distribution function? Let me convince you that it's actually related to this operator. If you were in coordinate space, the coordinate space for us was Z. We're saving X for something else. Then you could define the part-time distribution function as a proton matrix element of quark fields with a Wilson line between them. So they're on the light cone. And we have a formula like that. And also, one can convince oneself that if you want to write down for the antiquarks what the part-time distribution function is, it's the same formula as the quark formula, just with kind of an overall minus sign, and Z goes to minus Z. So that's an operator definition of the part-time distribution function. You can also define it by moments of the operator. That's the way that, for example, Peskin does it. But if you sort of put all the information in those moments back into a single operator, then it becomes this thing. And if we Fourier transform this, then it becomes the operator that we have up there. So there's something special about the matrix element we're taking here. And that is that this matrix element is forward. It has the same kinematics for the, so this is a collinear proton, but we have the same momentum here and here, right? In the in state and the out state, you have the same momentum. And that leads to one kinematic restriction on what I'm about to write. So what that imposes is that W1 should be equal to W2. So there's a delta function of W minus that comes from the momentum conservation or the restriction that it's a forward matrix element. But the sum of the two, with my sign conventions, it's W minus. The sum of the two is unconstrained. Well, it's bounded but unconstrained. So we can write the unconstrained part as this integral of C parameter. The bounding just comes from the fact that the quark can't carry more momentum than the overall momentum of the proton. Okay, so that's where it's bounded. It can't carry negative momentum, and it can't carry negative physical momentum. It can't carry, and it can't carry less momentum in the proton. That's where the limits come from. And then there's kind of two pieces. The W plus could either be positive, or it could be negative. If it's positive, remember, positive labels, that was our quarks. So this is the quark piece. And these are the antiquarks. They come with negative labels. Remember that we talked about that earlier. And so both the F and the F bar are hiding inside this formula. OK, so there is a simplification that there's this delta function here. And so basically what we're talking about then, you can think of just doing the integral over that delta function. So then you're talking about effectively an operator where you don't worry about putting a label on this one. You have only one delta function left, which I can denote by putting a label on this one. And this operator is actually exactly the operator that gives you the PDF. OK? This operator is like a number operator for quarks. Where you're thinking about momentum, a number operator with momentum omega. And if you want to think about there being some kind of field for a parton, this is about as close as you can get. OK, so this quark field dressed by a Wilson line is kind of like a parton in the parton model. All right, so next time we'll take this, put it together with this formula here, with the C, and just see where it leads us, and will lead us directly to a factorization theorem for deep inelastic scattering involving parton distribution functions and some hard, perturbatively calculable thing, which is actually a cross-section in the parton model. And then we'll talk about renormalizations with evolution. You can already see that we're getting the operator that I promised you, that DIS is described by this bilinear operator with two different quark fields and a particular labeling of the momenta.